we are for Lesson 3, writing products as sums and sums as products, and this is the first part of a two-part lesson. Alright, you're going to need a ruler. You'll be drawing several area models, so a ruler will help you draw straight lines. Alright, go ahead and take a look at the opening exercise. Complete the opening exercise on the lesson worksheet, and it should look something like this. If it's asked to solve the problem using a tape diagram, a sum of money was shared between George and Brian in the ratio of 3 to 4. If the sum of the money was $56, how much did George get? And again, continuing with our tape diagrams, if you drew these out and you made the boxes all the same, then George would obviously have 3 and Benjamin would have 4, and the total together would be 56. Well, if you count the boxes up, you'd notice that you have 7 boxes, and 7 units would equal 56. So therefore, one of those units would equal 8, and 3 of those units would equal 24. So George would receive 24, and Benjamin would receive 4 times 8, which is 32. Alright, so we're going to label one unit by X in the diagram. So that's going to represent one of the units in our boxes, or in our set of boxes. So what does a rectangle labeled X represent? Well, it's either going to be 8 units, 8 boxes, or 8 rectangles, depending on how you want to describe it. So draw in 8 smaller rectangles in the unit to represent $8. So you're going to take each one of these however you want to do it, but split it up into 8 smaller rectangles. You could do them on top of each other, or you can just split them up, cutting this 7 times. So in their representation, they went ahead and split it up by cutting it 7 times. So is it always necessary to draw in every one unit for all tape diagrams? No, it is unnecessary and pretty much tedious most of the time to draw every one unit. Tape diagrams should be representative of the problems and should be used as a visual tool to help find the unknown quantities. So it's not necessarily helpful to draw in every single one unit. Alright, so let's take a look at example 1. You can represent 2 plus 3 using squares for units. Well, you could either represent it in single unit squares and then show 3 plus 2, or you can make a rectangle that represents 3 and a smaller rectangle that represents 2. So now let's represent another expression, x plus 2. Make sure the units are the same size when you are drawing the 2 known units. So it looks something like this. If you had single units, they'd be the same size, and obviously there would be 2 of them. And x can be anything because we don't know what x is going to represent. So again, noting the size of the units that represent 2 in the expression x plus 2, using the size of these units, can you predict what the value x represents? Well, approximately 6 units. So now we're going to draw a rectangular array for 3 times the quantity of 3 plus 2. So when we do that, we take our 3 plus 2 and we triple it. But this time we triple it going the other way so that it makes a larger rectangle. So here's our original 3 units and our original 2 units, and then just triple it and you get a larger rectangle representing 3 times the quantity of 3 plus 2. So now draw a similar array for 3 times the quantity of x plus 2. So if this is representing x plus 2, again we would just triple it so that we have a bigger rectangle that represents the quantity of 3 times the quantity of x plus 2. So determine the area of the shaded region. Well, that would be 6, because if we have 2 times 3, this would be a total of 6 units. Determine the area of the non-shaded region. Well, if we have 3 times x, we would have 3x. So record the areas of each region. 3 times x is 3x, and 3 times 2 is 6. What this represents is a distributive property. 3x plus 6 is the same as 3 times the quantity of x plus 2. Note the key terms on your lesson worksheet and copy this into your math journal. All right, now it's time to do exercise 1. Complete exercise 1 by filling in the blanks. When you are done, go ahead and continue the video. All right, you should have exercise 1 finished. And you should have had 176 and 55. So now let's add the units. Obviously, you're not going to do this, but if you were to add each one unit, this is what it would look like. This would be one row of 16 and one row of 5, and then we have multiplied it 11 times. Is it easier to just imagine the 176 and the 55 square units? Yes, it would be way easier to do that. All right, let's take a look at example 2 for drawing tape diagrams for each part. So here is A. Go ahead and try this. How would we represent this as a tape diagram? We should have something like this. Notice that the length of x and y is arbitrary. We could have made x bigger than y, or y, as it is here, y bigger than x. But they shouldn't be the same size because they're representing two different quantities. But however you do it, you're going to obviously add them 2 more times. All right, how does this compare to what we have up top? Well, this would mean taking all our x units, putting them together, and then combining our y units and putting those together. And this would be 3x plus 3y. So essentially what we would have is the same thing. 3x plus 3y. We just kind of put them together. Our x's are the same and our y's are the same. Or we can also make a larger rectangular array and take each one at a time, put them together, and just show them stacked on top of each other. And then 3 times the quantity of x plus y would look like this. We would get rid of the lines, write this as 3x because it's 3 times x, and write this as 3y because it's 3 times y. Notice the progression that we've gone through here. All of these are representing the same thing. It's just how do you want to represent it? But all of these are equivalent expressions. So, kind of what I just got done mentioning, what can we conclude about all of these expressions? Well, they are all equivalent. So how does the 3 times quantity of x plus y equals 3 times x plus 3 times y? Well, 3 groups of the quantity of x plus y is the same as multiplying 3 with the x and 3 with the y. So how do you know the 3 representations of the expressions are equivalent? Well, the arithmetic, algebraic, and graphic representations are equivalent. Problem C is in standard form of problems B and D. Problem A is the equivalent of problems B and C before the distributive property is applied. Problem B is the expanded form before collecting like terms. Under which conditions would each representation be most useful? Well, either 3 times the quantity of x plus y or 3x plus 3y, because it is clear to see that there are 3 groups of x plus y, which is the product of the sum of x and y, or that the second expression is the sum of 3x and 3y. Which model best represents the distributive property? Well, that would be this model. 3 times x is 3x, and 3 times y is 3y. So therefore, 3 times the quantity of x plus y is the same as 3 times x plus 3 times y. All right, here's example 3. Find an equivalent expression by modeling with a rectangular array and applying the distributive property to the expression 5 times the quantity of 8x plus 3. First, you probably want to start with the 8x plus 3. But we could do this by showing that 8x plus 3 times 5 would give us 40x plus 15. So 5 times the quantity of 8x plus 3. That is, distribute the factor to all the terms, 5 times 8 and 5 times 3. So when we do that, showing our next step is to multiply. So 5 times 8 is 40, and 5 times 3 is 15. So now let's say that x is 2. We're going to substitute a given numerical values to demonstrate equivalency. So 40 times x plus 15 is 40 times 2 plus 15, which is 80 plus 15, or 95. Or the other way, 5 times the quantity of 8x plus 3 is 5 times the quantity of 8 times 2 plus 3, which is 16 plus 3, which is 19, and 5 times 19 is 95. So notice that both of these are the same. So since both equal 95, the expressions are equal. All right, let's try exercise 2. For parts A and B, draw an array for each expression and apply the distributive property to expand each expression. Then substitute the given numerical values to demonstrate their equivalency. Go ahead and try this and then continue the video. All right, you should have parts A and B done. Oh, we forgot parts C and D. You're going to apply the distributive property, substitute the given numerical values to demonstrate equivalency. All right, when you're done with parts C and D, go ahead and continue the video. All right, so here is for exercise 2, drawing an array and applying the distributive property. So if we have the quantity of x plus 1 multiplied by 2, that becomes 2x plus 2. And 2x plus 2, if we substitute x with 5, would end up being 12. All right, for the next one, 10 times the quantity of 2c plus 5, we would have 2c plus 5, and show that we are multiplying by 10. So 10 times 2 is 20c, 10 times 5 is 50, and we're going to replace c with 1. So 20 times 1 plus 50 is 70. For part C and D, just apply the distributive property. So 3 times 4f is 12f. 3 times negative 1 is negative 3. And if f is 2, then that means our answer, or our simplified expression, is 21. And for the last part, 9 times the quantity of negative 3r minus 11 is negative 27r minus 99, which is negative 369. Okay, example 4. Rewrite the expression 6 times x plus 15 divided by 3 in standard form using the distributive property. Well, that means in order to use the distributive property, we have to change division into multiplication, because there is no distributive property for division. So in order to do this, dividing by 3 now becomes multiplying by the reciprocal, which is 1/3. And when we do that, then we distribute the 1/3 by the term 6x and by the term 15. So 6x times 1/3 plus 15 times 1/3 is 2x plus 5. How can we rewrite the expression so that the distributive property can be used? Well, we can change from dividing by 3 to multiplying by 1/3. Right, try this with exercise 3. Rewrite the expressions in standard form. When you are done, continue the video. Alright, so you should have exercise 3 done. And dividing by 2 is the same as multiplying by 1/2. Now notice instead of writing the 1/2 at the end of it, they just went ahead and changed it to the beginning. That part doesn't really matter. You are still going to end up multiplying each term by 1/2, and you should end up with b plus 6. Instead of dividing by 4, it's multiplying by 1/4. 1/4 of 20 is 5. 1/4 of 8 is 2. And for part C, multiplying by 1/7. 1/7 of 49 is 7. And 1/7 of 7 is 1. Or in this case, -1. Okay, example 5. Expand the expression 4 times the quantity of x plus y plus z. Well, we just write x, y, and z, and a 4 on the left, and then show that 4 times x is 4x, 4 times y is 4y, and 4 times z is 4z. So the expanded expression is 4 times x plus 4 times y plus 4 times z. So what is the verbal explanation of 4 times the quantity of x plus y plus z? Well, there are 4 groups of the sum of x, y, and z. Alright, so now applying that to exercise 4. Complete the exercise, check your answer when you're finished by continuing the video. Alright, you should have exercise 4 completed. So, expanding the expression of 3 times the quantity of x plus 2y plus 5z. Again, across the top you have x, 2y, 5z, and down the left-hand side you have multiplied by 3. So 3 times x is 3x, 3 times 2y is 6y, and 3 times 5z is 15z. If you are doing the distributive property, then it would be 3 times x plus 3 times 2y plus 3 times 5z, which they're showing in the second step. And then by simplifying, we have 3x plus 3 times 2 times y plus 3 times 5 times z is 3x plus 6y plus 15z, which is the same as our visual. All right, example 6. Read the question and study the diagram. So what if S equals 4? How many tiles would you need to border the fountain? Well, there is a need for 20 tiles to border the fountain, 4 for each side and 1 for each corner. So here is our diagram. You need 4 between the 2 corners, 4 between the 2 corners, and so on. But what if S is 2? How many tiles would you need to border the fountain? Well, there needs to be 12 tiles to border the fountain, 2 for each side and 1 for each corner. So it would look like this. If each one of these is 2 feet, and then the one corner, 2 feet, and 1 for each corner, so on and so forth. What pattern or generalization do you notice between these two diagrams? Well, there is 1 tile for each corner and 4 times the amount of tiles, enough to fit one side length. So create three expressions that would find the number of squares. Well, you could do this 4 times the quantity of s plus 1, because if you take 4 times the sides, and then this would be s, whatever the side length is, plus 1. So s plus 1, and then you have this 4 times. So 4 times the quantity of the side plus a corner. You can also think of it as 4 sides plus 4. Because if the side length is between the corners, you have 4 of them, but you also have 4 corners that you know is 1. So the explanation, there are 4 sides of S tiles and 4 extra tiles for the corner. And last but not least, you can think of it as 2 sides, where we have a side plus 2 corners, and then we have 2 sides with no corners. So that would be a side length with no corner pieces. So this would be 2s, 2 times the side, because we have this side and this side. And then we have 2 times the quantity of s plus 2, which is a side plus 2 corners. So there are 2 opposite sides of S tiles plus 2 groups of a side of S tiles plus 2 corner tiles. All right. So what are some of the methods used to write products as sums? Well, we use repeated use of the distributive property in rectangular arrays. In terms of a rectangular array and equivalent expressions, what does the product form represent? And what does the sum form represent? Well, the total area represents the expression written in a sum form, and the length and width represent the expressions written in a product form. All right, we'll see you in class.